The stage is yours, Ondřej.
Thank you. Can you hear me well? Perfect. Thank you very much, Mr. Chairman. Good morning, everyone. Welcome to my talk, which will be about high-throughput workflow for heterocatalyst screening, employing trained machine learning interatomic potential, so kind of following what was said here in the morning, and actually a little bit following, maybe a little bit going with and a little bit against what Karsten was saying yesterday. So let's see how we will like it. I'm now at the University of Turku, but most of this work was done when I was here at the University of Aalto under Patrick Rinke here. So because not everyone is know the heterogeneous catalysis, I would like to kind of show you what are the motivations for this talk and for this work and what are the challenges there. So this kind of motivates us to go through this high throughput workflow. So the problem of the catalyst we have now, and remember that the catalysis is something that is consuming more than 1% of our total energy, which we produce at the Earth. So huge amount of something that we really need. For example, to feed our population, but our motivation was to go to something that is going towards green fuels, and that the methanol that we want to produce at this case study kind of is something that is mostly compatible with our today kind of gasoline-based infrastructure for, let's say, things that are moving. So the problem of the current catalysis is catalysts are low activity. What it means in terms of kind of, okay, can you see it? It's too slow. I wanted to, so the people on the internet want to see it. So the reaction speed is kind of defined by the barrier here, the energetic barrier. So what we want with the catalyst is to lower down the barrier as much as possible. At the same time, we want to have the selectivity. So on the left side, we have, for example, methane. So that's something we don't want that much in this reaction. So we want to go towards methanol. So we want that our catalyst would lower down the barrier just for one of the possible products. And the last thing that we will not talk about in the high throughput workflow, let's say, is the stability. So we want something that we put into the reactor and will stay there active as long as possible, because otherwise you need to either change it or kind of refreshen it, and this costs lots of money to the industry. All right. The problem that we have shown is that we have a huge material search space. And the other thing that Karsten was speaking about yesterday is the problem with the descriptors. So as he said, the current ones are not very good. So I hope that I will show you that at least for metals, we came up with something that is slightly better than what we have today. But let's start with something that we already know. That's the Sabatier principle. And so the Sabatier principle is pretty straightforward thing, is a simplified way how to look about catalytic activity, kind of mapping the activity with one adsorption energy per material. So we can be in different places here if you think about it. So the adsorption energy gives us how strong the, let's say, reactant binds to the surface. So if it binds too weakly, then basically the catalyst doesn't lower down the barrier enough. If it binds too strong, then consequently also the products will be bound to the surface or to the catalyst, if you wish. And that means that basically we are poisoning our catalysts with the product. So not good. And somewhere in between is the Sabatier optimum. Okay. But as we heard yesterday, this is not always the best kind of descriptor we can have. And why is it so? If you look at the industrial thermocatalysts, they look something like that. And unfortunately, this is not picture in operando, because in thermocatalysis, none of the techniques works at this temperature, unfortunately. But let's say this is how we imagine it, how it looks like as a computational. So we can have different nanoclusters on some support, and at this stage we are just looking at the nanoclusters there. So the supports plays a big role. Unfortunately, we cannot take it into account into our study. And so can we came up with something different? Because now you can see on the nano clusters there, we have different facets, we have different absorption side, and that was something that also Carsten was showing us yesterday, that the surface can also change. But okay, at this moment, let's just think about different facets and absorption side. So then we don't have, the material cannot be kind of mapped with just one energy, because the energy is different on these sides. All right. So the objective is for this kind of talk is to define a descriptor that is suited better for these types of catalysts, and set up a high throughput workflow that would kind of quick screen the possible search space before the experimental attempts, because at the end of the day, this is just a theoretical work, and we need to do lots of approximations on the way, so the real world matters. But what I wanted to add is something that we heard today in the morning, was the benchmarking, sorry. So we added kind of our own benchmarking to the study, because this is not inside the materials, but it's on a surface where the benchmarks are not that settled yet, I would say, at least. And because my colleague Prajwal has very nice poster on the other parts, how we kind of infer the results from this new descriptor, I will just quickly go to new material candidates for the experimental trials. Okay, so going beyond this Sabatier principle, what I showed 2 slides before, we were thinking, okay, we have these different sides, different facets. Can we look at literature that somebody else has to have similar problems? So we heard just before about high entropy alloys a little bit, or we saw them in one of the graphs there. So they are alloys of 4 or more metals inside. And then if you imagine each of the green, gray, and red thing here is ball here is a different atom, and that could be different element. So then each of the kind of binding sides, so we can have like on top on 1, 2, in a hollow 3, bridge side, or whatever. Then there you have different absorption energy, and that's what these people calculated there. So we have actually pretty similar problem here. So can we add it kind of to our workflow and look at different absorption positions and facets, like the on top, for example, on this nickel zinc on top of the green atom, nickel here, bridge, and the hollow here, and create the distribution of the absorption energies, and then try to learn something around it. Yes, as you can see, we can do it. We can calculate it pretty nicely. So, okay, this is some nice graph, colorful. Now, what to do with it? Let's first start about the good things about it. It considers local atomic structure. So if you think about some other descriptors, like for example MACPI, it's a great descriptor. But if you put diamond or graphite into MACPI, it will give you the same descriptor. While this one will consider the local atomic structure, and hopefully will be much more kind of suited for the kind of work that we are doing. The other thing that we were thinking about is it doesn't look unlike the Sabatier principle, where you take like few facets. We look at many more facets for simple materials, like let's say copper, we have just 6, but for some low symmetry materials, we can have up to, I don't know, 60 facets. And we kind of sum the things all over, because the facets, as we can see, can change during the reaction. So we kind of put this into account through kind of averaging all over of these. The other great thing, this is a methanol thermoconversion case study, but it can be pretty much tuned to any other of these similar studies. Because just the only thing you need is to find the step limiting reactants in the mean so you would add it as your adsorbate there. Yeah, and then it should, and I will show you that it shows you some similarity to the activity. But finally, and that what we heard here yesterday, today, and even the day before yesterday, it's computationally expensive if you think about the EFT. So what can we do about it? Because we didn't want to spend lots of time to creating our own MLIP at this stage. We took what was available at the time, and it was the OpenCatalyst project. So we heard about it, how it's really bad with some tasks. But anyway, it was the best on the surface. So far, so good. I will skip this, but it's trained on many millions DFT calculations. So pretty good for adsorbate surface analysis. And at the same time, what was important for us, there were available tools for automating creating the facets and adsorption positions, as I was saying here. So we get from our experimentalist kind of materials they wanted to test. They told us we can even synthesize it. Not that easy at the end of the day, but then what we did, we reached for something that is their materials project for the stable alloys. And then we use a little bit of DFT for bulk just to be on the same ballpark as the data in the materials project. On the OCP, because they were using RPB, so to be on the same level. And then we wanted to create the surfaces, but for many of the alloys which we had in the thing, we can have different termination of the same facet. So we can terminate it with the green atom or with the blue atom. The question now, which is that? We don't know in operando. That's the problem. We would love to do the things very right as Carsten showed us yesterday, but for the sake of the high throughput, we need to kind of find something that can be done quickly. So what we thought, okay, let's just add there something that is working in vacuum and just calculate the surface energies in vacuum. So that's what we did with the MLIP provided from the OpenCatalyst project. We calculate the surface energy, and then we chose the one that was lower, so the kind of vacuum approximation, so to say. And then, yeah, that's what I said already. And then we put the adsorbates on it and calculated all the adsorption energies. So far, so good. We are done, don't we? Well, what we wanted to add was to because lots of people at the time when we were starting the projects were just, showing that their data are working for just one material or two materials. Now we went through, now we have almost 300 materials calculated. So can we trust it outside of the regions or in all the materials? Can we trust it the same in all materials? So what we did, we took some special points, minimum, medium, and maximum for each adsorbated material, calculated on DFT, and did some estimation of mean absolute error. And then here you can see, yes, it is there, that the estimation is not 1-to-1, but it's pretty close, and it's still much better than what was done before. So we said, okay, let's take this estimation and kind of let's look at the data we have. And if the estimated mean absolute error is higher than 0.25 EV, which we set as a kind of cut line, then we removed the material out of the high throughput workflow. For all of the others, we compiled the adsorption energy distribution. So here you can see how the adsorption energy distribution looks like for a couple of materials. We kind of considered all the possible facets, averaged all over. No waiting for the facets area, because as we saw yesterday, the facets area are unknown in operando conditions. You can see that they can have different shapes, sometimes even the color-like switches, so maybe that can later tell us something about the selectivity, but I'm not going into it today. But for example, if we have very wide adsorption energy distribution, just thinking about the Sabatier's principle, it will tell us that it will be low active because most of the material will be not active enough or poisoned, and just few sites will be available for the actual conversion. But this is still multidimensional data, so how can we think about it? And it's something I have to skip for time's reasons. So this is 26 materials. We have now around 300 there. So you can see that it's very hard to comprehend by humans. So what we did with it, and that was part of the Prajval's post, but as not everyone could see it at the time, we used another unsupervised learning on top of it to find the new candidates. So you see there, the top one, we actually gave it to our experimental colleagues. You can ask me how it ended up. The other option is to kind of use some compression like statistical analysis on the AEDs, and you will kind of get a different type of descriptor, and you can kind of map it back to the Sabatier's principle. So what we've seen that all of these are around the copper zinc with absorption energies all over. This mean and lower than copper itself, which I'm unfortunately not showing here, which was found before that it's the best for the Sabatier optimum. And finally, what was our original idea was to combine the experimental data. We cannot do it because we find out that the literature is basically crap, unfortunately, because people tends to maximize something towards one benchmark, which was yield. But then the problem was that lots of other data were not collected properly and everything. So we are trying to work on it as well, but unfortunately it's not that easy. So with this, let me conclude my talk. I've showed you that the real-world catalysts are kind of hard to be described computationally and thus predict the activity. But what we tried is to find this new descriptor that gives us more information, and hopefully will be much better than what was there before. For high-throughput screening, you've already heard that MLIPs are great and much faster and everything, so that's what I'm saying here as well. But we should be careful what we are doing. So the benchmarking on targeting on your system is always very important, and validation of the procedure should be done finally at the end of the stages we heard from yesterday panel's discussion at the experimental level, because still this is just computational data, unfortunately. And that the further machine learning techniques are needed for the multidimensional data. And with this, I would like to thank Patrick and Prajwal and all the people who helped us, all the computational and financial support, you for your kind attention, and I'm open to questions.
Thanks, Ondřej, for staying in time as always. Do we have some questions? We have time for maybe one or two quick ones. You want to go there and I go there.
Thank you, Ondřej, for a fantastic talk. Could you let me know a little bit more about the last step when you mentioned the unsupervised learning and finding similarities between these compounds? I didn't catch which method exactly did you use?
I haven't told it because that was part of the Prajwal's poster, so I didn't want to, and most of his work, so I didn't want to go into it. But what we did was hierarchical clustering, basically based on, do I have it here? Based on Wasserstein distance here. So we take the data which we had, put it to one long vector, make a Wasserstein distance between those long vectors, and then do the hierarchical clustering, and that what we kind of got. So these are 159 materials that we found, and just 2 of them seems to be promising out of it. Maybe there are more, but as we don't have the greatest point which we wanted to kind of go, we kind of go in the evolution, not the revolution, because we are looking what is similar to something already good. The good thing about the new catalyst is that possibly it's more stable because it has a higher melting temperature. But nobody asked about it, but I will tell anyway that the problem with the higher melting temperature is that our experimental colleagues didn't have possibility to kind of prepare the material because they needed to heat it up, and they didn't work with their setup. So unfortunately, so far is a failure in experimental way, but we hope that it's just because they couldn't make the alloy itself.
You mentioned already need to, the proof of it experimental data. And is there any comparison with the literature already?
So there are few data sets available on the internet. I think there are 2 possible. None of it is properly machine readable at the moment. So we are working on that as well, and some of them are still missing some data, and we hope that we will do a better job, so to say. And I think that one of the message for the community, unfortunately, of mainly experimentalists, which I admire that work, but they should be better in kind of labeling there and making the database by themselves, because it will be much better. And the problems, for example, for LLMs is that people use very much different units and different ways how to also slightly different terms, like something is volume, something is mass, so we need to convert lots of things around. So I hope that in the future, what drives us computationalists was a lot where the new databases like Material Project, Alexandria, which we heard before, this helped us a lot. So there has to be something for the experimenters as well, and this will help them hopefully much better.
And one question was, we are interested to hydrogen production using of 2D materials or the metal alloys. Do you know any idea about hydrogen production or something?
Unfortunately not.
Okay, any further questions Ondřej will answer, and happily will answer in the coffee break. And let's move further, and thank Ondřej again.